So let's start the today's session. So in the previous classes, we studied or we started with the lexical tokens, lexical tokens we can say, or lexical conventions we can say. So in that we studied white space, comments, operators, then the number specification. In the number specification, we studied some two different number specification. The one is a size number, the another one is unsized number. How to use in the Verilog tutorial. The next lexical convention is we are going to study is identifiers and the keywords. Normally the keywords are special identifiers. It's a reserved word we can say in the system. Normally we cannot use the keyword as a identifier. So in the system if you see the keywords are will be given in some like colors in system if you see. So that will be used to define the language constructs. So normally the keywords are case sensitive. It's a case sensitive. You have to be very careful. It's a case sensitive. Normally will be in the lower case only. But when you go for the identifiers, the names are the user defined names. The user can write any name, whatever. But very careful. The identifier cannot be used as in the sense the keywords are cannot be used as identifiers. You should not use the keywords as the identifiers. So you can use any identifiers. For example, you can say the identifiers are be made up of some alphanumeric character like such as underscore, or you can say a dollar sign also. The next word you can say the identifiers also case sensitive here. Then normally the identifiers will start with the alphabetic character or an underscore actually. Normally, the identifiers will start with the alphabetic character. So example, I can say you return the program, the module name. One example I'm saying the module name is the identifier. So we said what are the rules you have to follow to write the module name over the ICF, right? So the identifier should be start with the character or an underscore only, but they should not start with a number. So very simple, I can say the identifier should not start with number or should not start with a dollar sign, especially because the dollar sign LB is reserved for system task function in the Verilog HDL. So that is what the dollar sign we use. Later we use, earlier I might have shown dollar display. You can remember that. So that is what we use. The example I say here, register REG, register the value. Here the value is here identifier. The register REG is here keyword. Same here. Input clock. The input is here keyword. Input is a keyword and clock is a identifier. So like this we can write then how we should not write. That is what already we discussed in our classes and all. Let me show here if I write like this. See, if I say like HA underscore adder. If I add, so this is correct I think. But if I write like this, identified, if I write like this, then this is wrong. The reason is it is started with the dollar sign, or it should not start with like this, like I say in this way. Like I'll say as like this 4-bit adder. Say example, I'll say if I write like this, then this is wrong because the identifier starts with number, so it should not be start. So like this should not write. Now escape identifiers. Next to the escape identifiers are start with the backslash character. That is this one. Which one? The escape and this one. Backslash characters we have to use. Then it provides the meaning of including any of the printable ASCII character. You remember in your C program, you will write the printer statement. In the printer statement, you will write in the last finally the /n /tab. You remember that in the initially we studied the white space slash new line. So next we studied /b for a backspace, then /t for a tab, then /n for new line. So that slash only we can say to use for escape identifier that provides the meaning of including any of the printable characters in an identifier. Here, the decimal values 33 to 126 are 21 to 7E in hexadecimal. So, it's printable the ASCII characters in an identifier. The decimal value will be this. So, now an escaped identifiers ends with white space. See, why we are saying white space in the sense, the examples already which we studied, that is nothing but examples are what? Slash B, that is blank. Next slash T, that is tab. Next slash N, that is for new line. So here this slash special escape identifier followed ends with white space. This is the white space actually. Next, neither the leading backslash character nor the terminating white space is considered to be part of the identifier. So, like normally what we'll do, so we can write leading backslash character, not terminating white space. Here sometimes we will use, so that also will be part of the identity. Even this also I can say is a part of the identifier only. So now, sometimes the escape identifier should not be used for normal circumstances. Sometimes we won't use actually this one. So very simple example here you see slash a plus b minus c slash double star my name slash then backslash. Even you can write the identifier here also. See this slash star. So these are the ways, different ways you can write the escape identifier. It's followed by some identifier. That is the backslash with some identifiers also we can write. Now next is the very important concept in the Verilog HDL. So here like one of the main important questions in the in our VTU, that is the Verilog data types. What are the different data types in Verilog and explain you may ask. So now here the data types in Verilog are classified into different types. Here that is nothing but value set, then next registers, vectors, integer, and real. So these are the data types we are going to study. Then additional real, then time register, arrays, memories, parameters, strings. See there once again, I say value set, nets, register, vectors, integer, real, time register, arrays, memories, parameters, strings. These all are the data types in Verilog. So let us study each and every one data type here. First, value set. What are the values the Verilog will support here? The Verilog will support 4 values. This already we studied under 8 strengths to model the functionality of real hardware. So here, what are the value sets in the sense value levels are? You can see the value levels are 0, 1, X, Z. These 4 value sets will be support, the Verilog will support these 4 values. But what is the condition in hardware circuit? When I give the value level 0, that is represent as either logic 0 or false condition. Then 1 means logic 1 or true condition. Then X means it's an unknown logic value or it's unknown value I can say. The Z is something with the high impedance or sometimes they may call floating state. But as you know, this X and Z normally will be used in the real circuits for the real time circuit. At the time only we can get this X and Z actually. So now what is the strength level here we are having? Here we are having so many strength levels are there. See here, these are the strength level which we says here. So example, the strength level will start from supply, then here the last is high Z. So these are the strength levels we specify in a Verilog: supply, strong, full, large, weak, medium, small, high Z. These all are keywords actually. Remember, these all are keyword. The supply actually we use for to type is nothing but driving in the sense like normally when you are going to write the program in the switch level model, that is nothing but the transistor based Verilog programming. If you write at that time, we'll use the supply 1, supply 0. That indicates the supply 1 means VDD because VDD value and the ground value, how we can provide in the program. For that, we are having a separate keyword that is supply. Supply 1, if I give, that will become as VDD value, that is VCC. Then supply 0, if I give, that will become as ground. Normally, ground will be 0. That is why we say it is a driving axis. What is the degree? The strongest one actually. Strong, that is also driving. Full. So this is so you can say the high is that the high impedance is weakest, the supply is the highest degree normally. This is the hierarchical come. So very important here, if two signals of unequal strength are driven on a wire. So example, you consider some two wires are there. Like example, let me take example. Okay, now we will see the value sets, right? So in the value sets, let us take the example as like this. If two signals in the sense, I will draw one AND gate. Example, let me draw a one AND gate. You think here one value, here one value, right? Two signals of strength, strong one. You think this is strong one, this is strong zero. Actually, strong one or weak zero. So I will say yes. Yes, one means strong one. This is weak zero. Why? Because what they said actually, if two signal of equal strength, unequal strength, they said, right? The unequal in the sense, strong one, weak zero, I can say. The content, what will be the result now? See, it's a strong one, then weak zero, then the output will be strong one, actually. Because we are having strong one, strong zero, weak one, weak zero, like this, different values are there here actually. So this is the one thing. The strong I said no, so this is actually, you can see here we are having in this here strong. It is also a driving type only. See, the supply also is a driving type only, strong also is a driving type only. So we'll get like this. At the same time, if you are having two different, say example, I'll say like this. I doesn't know, as I said here, AND gate I drawn by mistake. Just you think as this is not AND gate, some box. You think I doesn't know what is the operation is performing over there. So now here, if I say if two signals of equal strength in the sense I can say S is equal to 1, that is strong 1, then strong 0. Both are equal strength in the sense are driven on a wire, then what is the result? Normally the result will be X. I'll get that. Now you can set another example. If you are having examples like two signals here, if two signals of strength, strong 1, then strong 0. So here I can say signals of strength are driven on a wire. Wire in the sense what? This is the net, I can say equal strength 1, 0. Then if two signals of strength strong 1 and the strong 0, it conflicts the same thing X, I said. Then I can say one more thing is, so like this, different values will be there. I can say X1 even that also. So normally this will be used in a mass. Normally, but very careful. So the mass devices, dynamic mass and other low level devices only will use this kind of values. Which are it? The supply 1, supply 0, strong 1, weak 0. All these things will be used in a mass devices. The only tri-ridge, that is the one more data type is nothing but the tri-ridge. See, this is the keyword actually. Tri-ridge net can have strong storage strength large, medium and small. This is tri-ridge in the sense the register will have three states, will have like in the sense 0, 1, X. It will have these three actually, large, medium, small. Next is something but nets, which we can call net in the sense nets are wires. Normally, the nets are wires, we can say. The nets represent connections between hardware elements. Is it visible? The screen is visible for you? The nets represents the connection between hardware elements. As I said, the nets are like this. See, hardware between the hardware elements in the sun. Here, one block we are having. Here, we are having the another one more block. Then I can say, if we are connecting with this one, so this only I can call as net. So, or I can call as wire. Net or wire we can consider. That is why I am saying the net represents the connection between hardware elements. That is interconnection between output of the one component to the input of the other component. That is what I said. So it's just as a real circuit. Net have values continuously driven on them by output of the devices that they are connected to. So very important here you can see the value of the wire can be read but not assigned to in a function or a block. Normally the wire values you can read but you cannot assign in a function or in a block that wire value. Very important thing, one more thing, the wire does not store its value but it must be driven by the continuous assignment element or by connecting the or by connecting into output of gate module. So example, say here we are having one gate here, right? So next we are going to connect one OR gate here. Then here one more AND gate, OR gate, anything you take it. Okay. Now we'll see this is what has happened. This AND gate will be driven from this AND gate actually. Now when this will value it will get changed whenever this value get changes, immediately this value will get changed. So this value will not be stored. So same the way even here also like this. So that is why I said the wires will not store any value. It will give the immediate response. At the same time, I cannot assign any value for this because how I get this value in the real circuits normally based on the input. What are the previous signal here? What are the value given? Based on it will compute, then it will give. I cannot assign any value over there, especially in the real circuits actually. In the function block or in the blocks, we cannot. That is what I can say nets. These are called as nets, we can say. The example here, there are two group of types in the nets. Net data type, the another one is called as variable data type. We can say two different. We can say in this figure, see the net A is connected. See, this is a net actually. The net A is connected to the output of gate 1. Here the gate 1, here G1 is specified. The G1, the net A will continuously assume the value computed at the output of gate G1, which is B and C. That is nothing but, what is that? That is nothing but, let's say here it will be like this, right? A is equal to B and C. This is what. So now this A is nothing but of your output of a gate 1 G1. The B and C are the input of gate G1. So this will be computed, then this will be assigned to A. This is what I can say, it's net actually. This is net. This is also net only wire we can say. Otherwise, see here another one more. So you can declare a net for a given circuit here. One simple example is shared, that is nothing but wire. See here, wire A. This is we are declaring as a wire because if we consider this is the main program, then I'll say input, this is the output. But you may think somewhere in between, intermediate. So now wire A. Next, this also is a wire B. So you have to assume from previously we are getting this is connecting to the another circuit. You have to assume in that way. Then wire D is equal to 1 dash B0. Even you can assign the value for wire. See here, we can assign. So the D is assigned as 0. If it is scalar, you can assign like this. If you want to assign the vector, then you can assign like a 2 dash B 0 0. You can assign like this also, but you need to specify here like 1:0 D is equal to 2 dash B 0 0. So the D is a fixed to logic value at declaration. Even you can write like this also. See how we can write in the sense? We can write like this also. As I said, where 1:0 A equal to 2 dash B 0 1. Even you can assign like this also. This is like the assign only. They are assigning the values. Now, an identifier of net data type means that is must be driven. The value changes when the driver changes the value. So the identifiers are what? This A, this B and C are identifiers actually. So once the identifier net data type means that must be driven. So if I specify wire A in the sense that might have or must be drive the another circuit. For example, I can say here in this circuit wire, see this is what the diagram is given. Now actually the diagram is given this only. So now what I'm going to do, see example, you assume as something, some circuit is there. Here some circuit is there. So now this output is giving over there, this output is giving over there. Then we are having the one more circuit, we doesn't know what circuit it is. Then this will be here. Then we doesn't know how much input and how much output will be there. Now you can say this is actually as per the previous diagram. This is A, this is B. Now you can see the C is driving the another one. This would be some other output, something called as Y. Now see the input also is driven from some other circuit actually. That is what they said. It must be driven. The value changes when the driver change value. That is why I said when this value get changed, when this value and this value get changes, automatically even this value also will get changed. That is what they said. Now the syntax for that wire is wire underscore name. That is a wire name is equal to this is a value. This is already we written in our class actually. So note. So you note that here the net is not a keyword but represent the class of data type such as wire W NAND. Be careful here. Something new is there now. Wire W and WR, that is W and means wire and WR means wire R. This is try and try R, then try ridge, etc. So many things are there. Now you see the nets are declared primarily with the keyword wire. See? With the wire, the nets are declared. You need to declare in the sense you must use the wire actually. The nets are 1-bit value, very, very important. It's a 1-bit value by default actually, unless they are declared explicitly as vectors. If you are not declare any vectors by default, the wire will be considered as 1-bit value. The term wire and net are often used interchangeably. Don't get any confusion. Wire, net, both are same. Net is equivalent to nets is equivalent to wire. Don't get any interchangeable. Sometimes we may call it net, sometimes we may tell us wire. Both are same only. The default value of Z, very important, because default value of wire is a default value of Z actually is nothing but net is Z. Very important. The default value of net is Z actually. Default value is high impedance, except tri-reg net. Here we use tri-reg, no? The tri-reg net actually, which defaults X actually. So next, the net gets the output value of the drivers. If net has no driver, it gets the value Z. Like if net in the sense wire, if wire that has no driver in the sense, if it is open, I can say simple. If I say like this, see, we are having AND gate like this. So here we are having like this. This is the output, but this will be connected to something circuit. Then this also is something connected, but this is not connected. It's open. You think as this is open. Now at that time, what will happen? If it is open, means it will be considered as X. That is what we said actually. This is the default value to be X. So no driver, the get value will be Z actually here. That is high impedance. So now the identifiers basically represents wires and are used to connect components. That is net data types are wire, supply 0, supply 1. This is what I said earlier. Supply 1, supply 0. Try and try or try 0, try 1, W and WOR, strong 1, strong 0, full 1. That is, you are going to put the value weak 0, weak 1, high is at 0, high is at 1, small, medium, large. So these are the some basically represent wire are used in the connected component. W and means already as I said, it's a wired and W and means the value of W and dependent on logical and of all the drivers. Like W and means it performs the AND operation. WR means it's a wired R, it will depend on the logical R of all the drivers connected to it. Tri means it's a three-state actually. Tri means three states. So all drivers connected to tri must be Z except one, which determines the value of tri. So all the drivers connected to tri must be Z, that is high impedance will be there. Normally we say input will be 0, 1, X sometimes, but output will have normally Z also will be there. See here, this is the truth table which is specified here. This is the truth table. Now, what I will do, let me take a simple example how we are going to use this first, then we'll see go over there. Okay, let me take an example here. Example for next. Okay, let me take some example here. Now, module using wire A, B, C, D, F. Simple I'm using. Then our inputs are A, B, C, D. Input. Then output is Y, F. Then I'll say a little bit example wire F. Now let me write assign with the using of assign statement. Assign. You don't think what program, just I'm writing the example, it can be any program. F is equal to A and B. Assign F is equal to C or D. Then end module. You see, what about this actually? This is the diagram. Let me say how this diagram actually, this diagram is A, this is B, right? AND gate. This is A, this is B, A, B, this is F, okay? Next, C, D, R gate. C, this is D. Now, this is the given circuit. For this, we need to write the program. Will it execute properly, this circuit? Will it give the output, proper output, this circuit? Do you think the program is correct?
Capital F it will provide.
Capital F in the sense, just assume even this also is capital F only. You can say this is also capital F only. You can, I'll erase this.
We need to add the, we need to sort it.
Just you have to try out. Now, what will be the problem actually if I give? See, both the outputs are sorted here, AND gate, OR gate. But I cannot say the F will give you which output, whether this AND or OR. So I can say this is wrong. It won't provide any proper output, right? When I write the program as like this. Right. So now what I should do, I need to correct this. How can I correct this? With the modifying this program, I can do. What is the modification I will do here? Same module using wired and A, B, C, D, F, input A, B, C, D, output F. Then what I will do, instead of writing like this, I will write like this. W and F. Then assign F is equal to A and B. Then assign F is equal to C or D. Then N mod. If I give like this, so we will get the output actually. The reason is here I used wire here, right? Here I used wire, but here I used wire, but here I used W and. So what is the meaning of W and in the sense? What it will do? You may have the question. What it will do exactly? This will do like this. W and F will do like this. F itself is equal to A and B. It will perform. Net F is declared as, see, the net F is declared as W and. So it will perform the operation. Which one it is like internally this diagram will be changed as like this. In between here, this place we will add one AND gate actually, then will be F. If I write like this, by inbuilt, the system will consider like this. So your diagram will become as like this. How it will be? The diagram will be like this. See, this is the F actually. This is your A, this is B, this is C, this is D. So now this will be a W and. See, this is W and. So I hope it is clear for you now. The same like that you can see some of the, this is a truth table. We can see how this truth table is done actually in the sense we can see try or wire. These all are inputs. This also a input. See here this also is input. It's also input. When I give try, so what will happen here actually with the wire try states. So this will give you the tri-state like when 0, 0 will be 0, 0, 1 is x, 0 x means x, 0 z means 0. Like if you are having any block, both are equal strength. 0, 0 means it will be given as 0. If both are 1, 1 means it will give us 1. If any one input is x, then it will be unknown. If any one input is high impedance Z, then the output will be 0. That is what it specifies. I hope you might have understood that. First